We saw some new terms towards the end of last week, and a lot of those terms were somewhat alike to one another here. So we want to spend a few minutes today just distinguishing between those terms, making sure we know what each of those meant. First one we had was electric potential energy. If you remember last week, the electric potential energy in a system was the energy stored in that system of a couple charges a certain distance apart. So you got these two charges, there's energy stored in that system. They either want to attract or repel, and that energy is that energy of attraction or repulsion between those two charges a certain distance apart. But then we talked about electric, by the way, the symbol for electric potential energy, we just say was EP. Then we talked about electric potential energy difference. So almost the same thing, but we tossed in one more word, electric potential energy difference. Delta EP. Electric potential energy difference is the difference in energy stored in that system of two charges a certain distance apart when we move something. Okay, when we change the potential energy because we change the distance or we change the charge, that change in potential energy is delta E. Now, what's that also equal to? What's another symbol that we could apply to delta EP, the change in potential energy? Think about this, work hard and you might get it, okay? What is it? Work, yeah, it's the work. The change in potential energy is the work done in moving a charge a certain distance through that electric field. Then we talked about electric potential. Doesn't sound like there's much of a difference between potential energy and electric potential, but there is. They're similar, but there's a significant difference between the two. What are we talking about here, Ethan? Yeah, it's the energy per Coulomb of charge. Remember on Thursday or Friday last week, we gave you the analogy of the money. We're going to 7-Eleven. Okay, we got 25 people in the class. We have $100 total in the class. The energy would be $100. Okay, but the potential would be $4. $100 divided by 25 people gives me $4 per person. Potential is the amount of energy per Coulomb of charge. And the symbol for that is V, a capital V, not a lowercase, because that would be speed. Capital V. And we find that by taking the potential energy and divide it by the amount of charge. So the amount of energy per Coulomb of charge, not the amount of energy, but the amount of energy per Coulomb of charge, E over Q. And then we talked about electric potential difference. You guys remember what the symbol for that was? Potential is V, then potential difference has got to be what? Delta V, right? And we can find delta V by two ways. One, we can say it's VF minus VI, it's the final potential minus the initial potential, but we can also say, in the way that it appears on our data sheet reflects this one, delta E over Q. If V is E over Q, then delta E will be delta V over Q. All right? So electric potential energy difference, potential, and potential difference. Let's keep all of those straight. Okay, and understand when we're talking about one of them, which one do we mean? Do we mean V? Do we mean E? Do we mean delta V? Do we mean delta E or W? Okay, let's keep all those straight and we should be good. None of them are crazy hard. It's just a matter of keeping them straight. All right, we had a couple of questions, I believe it was, for homework on, I think it was 561 here. 565, actually, I have written down here. Was it 565? Okay. Yeah, there we are. There we are. Do you want to go over one of those, two of those? I mean, we should go over one of them at least, just to make sure that you guys are all good. But Rosie, second one? Anybody for the first one? Yeah, okay. First and second one. Let's say number one, in moving a charge of 5 coulombs from one terminal to another, a battery raises the potential energy by 60 joules. What's the potential difference between the battery terminals? What do we got given to us here? This is charge, right? 5.0 coulombs. Some 60 joules. What is that? It raises the electric potential energy by 60 joules. Is that Potential energy difference, potential difference. It raises the potential energy. What's it going to be, Ollie? Not potential difference, but you're close. Potential difference would be the energy per Coulomb of charge. So what would it be? Yeah, it's potential energy difference. That's going to be delta E, or we could say W, because it's the same thing as work, right? We want to find the potential difference. Well, odds are for this one, we're just going to say delta V is equal to delta E over Q, using the equation that's on our data sheet. 60 joules divided by 5.0 coulombs, it gives us a total potential difference of 12.0 joules per coulomb. Good? What's another set of units we could use to replace a joule per coulomb here? We don't like writing joules per coulomb. We want to write something that's a little bit more familiar to us. Volts. So 12.0 joules per coulomb, 12.0 volts, both work for us here. All right, good. 2. A charge of 2 times 10 to the minus 2 coulomb moves from one charged plate to the oppositely charged plate. Here's the potential difference. What's the potential energy gained? What do we got given to us here? Q is 2.00 times 10 to the negative 2. The potential difference, so it's 500 volts. What is that? Is that E? Is it delta E? Is it V? Is it delta V? Or W? The potential difference between the plates is 500 volts. Guess what do you say for that one? Yeah, it's going to be delta V, the potential difference, not the potential energy difference. That would be delta E, but the potential difference, and it's going to be delta V. We want to find the potential energy gained. What are we looking for then? E or delta E or V or delta V? Delta E. So we're going to say delta V is equal to delta E over Q. Let's rearrange that. Delta E is equal to Q times delta V. And we get 2 times 10 to the minus 2 times 500. And that should give me 10 joules, I guess. Clearly, the mathematics of these questions are easy, right? Easy. It's just a matter of recognizing what variables you've got. Put them in the right place. Let's try this example on page 566. There's a small charge of 3.2 times 10 to the minus 19 coulombs. Maybe it's an alpha particle. Maybe it's just some object that has that much charge because it has 2 less electrons than protons. Whatever. Moving to 2 parallel plates with a potential difference of 2,000 volts. Oh, wait. Not a potential difference. It says the electric potential is 2,000, and then the electric potential is 4,000. Oh, it doesn't even ask a question, though, does it? The question should have said, what's the potential difference between the 2 positions? And question B should have said, what's the potential energy gained by moving the charge? Not the potential difference, but the potential energy gained. And they were looking for that in joules, and they were looking for that in electron volts, which we talked about briefly on Friday. All right, let's get the potential difference first. What do we have given to us here? We got a charge of 3.2 times 10 to the minus 19 coulombs. We have, what's this 2,000 volts thing here? Is that electric potential energy difference, potential, or potential difference? Ethan? Yeah, that's going to be potential, initial potential, capital V-I. Not initial speed, but initial potential. 2,000 volts. My final potential is going to be 4,000 volts. We're looking for, first of all, we're looking for potential difference. So all we're going to do there is subtract the two. 4,000 minus 2,000 equals 2,000 volts, or we'd say 2.0 times 10 to the 3 volts. Okay, there's the potential difference. Now the potential energy gained, what are we looking for right there? Potential energy gained. E, delta E, V, delta V. Not going to be delta V, we already added that. Yeah, go ahead. Yeah, it's going to be delta E, the potential energy gained here. And all I'm going to do there is rearrange the equations on my data sheet. Delta V is equal to E over Q, delta E over Q. Rearrange and solve for delta E. What do I get? 3.2 times 10 to the minus 19 times 2,000. Do the math there, and it should work out to be, I believe, 6.4 times 10 to the minus 16 units. Joules. 2.0 times 10 to the minus 16 joules. Now, they wanted it in electron volts as well. You might not remember what an electron volt is right now, but if you check your data sheet, it tells you. On the left-hand side of your data sheet, it says 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. You guys remember that? Yeah, it's in your notes, but we did it kind of in passing towards the end. If you don't remember, that's okay. Check your conversion factor on your data sheet. 1 electron volt is equal to 1.6 times 10 to the minus 19. The easiest way, in my mind, to solve that is to actually set it up as a ratio. I know that 1 electron volt is 1.6 times 10 to the minus 19 joules. If that's the case, then X electron volts will be equal to 6.4 times 10 to the minus 16 joules. That make sense? If 1 is to 1.6, then X is to 6.4. Solve for X. And when we do that, I think we end up getting is it 4,000? Which technically should be rounded to 2 digits. 4.0 times 10 to the 3 electron volts. Listen, electron volts is a unit of energy just like joules is. It's just a different unit of energy, that's all. Just like meters per second is a unit for speed and kilometers per hour is a unit for speed. There's just 2 different sets of units. Sometimes one is convenient, sometimes the other is convenient. Now we have 2 sets of energy. Joules and electron volts, sometimes one is convenient, sometimes the other is convenient. A couple practice problems that go along with that. We'll give you just a few minutes here, maybe 4 or 5 minutes to see what you can do with those questions. And then we'll move on to a couple multiple choice. And then we're going to move on to our last topic of the unit, which is not brand new, just an extension of what we've been doing, but a little bit further than we've already done here. See what you can do with these now, please. Okay, let's take a look at question number 2. It says an electron moves between 2 positions with this potential difference. What's the potential energy gain? Listen, this is a bit easier than the example we did, right? Because we already have the potential difference, delta V. It's 40,000 volts. We also have, we're talking about an electron, so we also have the charge of the electron. It's 1.60 times 10 to the minus 19 coulombs. It's actually negative, but we know that when we plug it into an equation, we're going to drop the negative sign, because we always do. We're looking for the energy gained. The potential difference is 40,000. The potential energy difference is what we're looking for here. So we're going to rearrange the equation. Delta V is equal to delta E over Q. We get delta E is equal to Q times E. Q times delta V, I should say. And what do we get? 1.6 times 10 to the minus 19 times delta V is 40,000. What do we get there? 6.40 times 10 to the negative 15 joules. There's our answer in joules. Whenever we're using this equation, we're going to get an answer in standard units, which is joules, not in electron volts. But then, in this case, at least, we got to convert it to electron volts. So, we're going to say from our data sheet that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. Find that on your data sheet. If you haven't looked already, go to your data sheet, find where it says 1 EV equals 1.6 times 10 to the minus 19 joules. Then let's set that equal to X electron volts over 6.4 times 10 to the minus 15 joules. When we solve for X, we end up getting 40,000, or 4.00 times 10 to the 4 electron volts. Now, it's the same number as we had here for the potential difference. Is that a coincidence? Partially a coincidence, but not entirely. because of the way we define an electron volt, which is the energy gained or lost by an electron through a potential difference of 1 volt, when you're dealing with an electron, the potential difference will always be the same as the electron volts. But if you're dealing with something other than an electron, like an alpha particle, let's say, with a different charge, then they won't be the same number. So it's kind of a coincidence in that it's not always the same number, but if it's an electron, it is always the same number. So partially not a coincidence. If you've got an electron, then the electron volts will always be the same as the number you got for potential difference. But I wouldn't try to memorize that, because in the end you can figure it out like we just did, and you say, oh, it's the same. All right, that makes sense. That makes sense because it's an electron, right? It would be the same for a proton because it's the same charge. Yeah. Julie, is that okay? Good there? Okay, I got a couple of multiple choice questions I'd like you to work on. They are multiple choice 62 and 63. Both in your worksheet, in your booklet here. Sorry, actually, 61, 62, and 63. 61, 62, 63. All going with this information that you see prior to those 3 questions. Right now, I would like you to do 61 and 62. Leave 63 for now. We'll do that one in a couple minutes. 61 says, when the neutral pith ball was placed near the charged Van de Graaff generator, the pith ball was attracted to the generator as a result of, what is this going to be? Charged objects attract neutral objects because of induction. It's specifically a temporary separation of charge, right? For the general category is called induction. So the answer for number 61 is A. 62 says, the direction of the electric force on the pith ball is which way? Well, if the pith ball is attracted toward the Van de Graaff, then the direction of the force on the pith ball must be the direction that it's attracted to, right? Towards the left, which means the answer for that one is going to be B. How many people got B for that? Good. I want to give you just a couple of minutes to take a look at 63. It's a hard question. It's a serious challenge question here, okay? I want you to see what you can do, see if you can come up with an idea for a couple minutes, and then we will definitely go over this one as a class. If any of you happen to get it, good for you, okay? Because it's a big challenge question. If you don't panic, but pay close attention when we go over it as a group. All right, let's have a look here. We want to find the magnitude of the electric force acting on the pith ball exerted by the Van de Graaff generator. We're going to go back to the page here because this is what we really need in order to solve this question. The magnitude of the force. I'll be honest with you, the first time I saw this question, and this question appeared on a diploma exam about 13 or 14 years ago, maybe even more, it might have been 15, 16 years ago, somewhere in that range. The first thought that I had, well, listen, you want to find the electric force? F is equal to K, Q1, Q2 over R squared. Anybody think like me there? Was that the first thought that you had? There's nothing wrong with that thought. It doesn't do anything for you. It doesn't help you. But there's nothing wrong with that thought. And the electric force is equal to KQ1, Q2 over R squared. And I realized, though, that I can't do that because I don't know anything about charges. In fact, one of them is neutral. So that's not going to help me at all, even though it's valid. So then I thought E is equal to F over Q. Right, the experienced or equation, that universal equation that we have for electric fields, rearrange it to solve for F, it's Q times E. And then I was, wait, I don't know Q or E, so that's not going to be helpful to me either. So then at first, I was at a little bit of a loss when I did this question for the first time. Like, what do I do now? I got 2 equations for electric force. I don't know anything about any of them, so I can't do it. So what do I do? Well, then I just started trying stuff, and that's what I do when I'm struggling with a question. Is I just start trying stuff. But what I should do, at least when I'm just trying stuff, is try not random stuff, but try valid stuff. So what I tried doing on this one is drawing forces, just trying to figure out what was going on here. The force of gravity acting down on the pith ball is m times g. Agree? Okay. There is an electric force acting this way, and that's what we're trying to find, right? Although we don't know what it is, but that's what we're trying to find, that electric force. But we know that there's a force of tension acting this way. tension in the rope acting this way. Look at this, guys. This is similar to a question actually so far that you had on your assignment. If this pith ball is not going to move, there has to be an upward force canceling the downward force. There has to be a rightward force canceling the leftward force. Otherwise, this thing would not be at rest. It would be moving. And then it occurred to me. It wasn't until I had this diagram drawn that it occurred to me. I didn't draw the diagram because I knew where I was going with it. I drew the diagram because I didn't know what else to do. Then it occurred to me. If it's suspended and these forces have to balance, then this force, the X component of the tension, must be equal to the electric force. And the Y component of the tension must be equal to the gravitational force. Right? The upward force equals the downward force. The rightward force equals the leftward force. If I know this angle right here is 20 degrees, and I know this side is m times g, then I can find this side by using a little bit of trigonometry. So all it ends up being, tan 20 degrees is equal to opposite over adjacent. Fe ends up being equal to, what's m? 2.5 times 10 to the minus 4 times 9.81 times 1020. And I'm not sure what that actually works out to be. If I 6 times 10 to the minus 4. Anybody happen to get that? Listen, there was a period of time since they put this question on there that they were throwing questions a lot like this one on the exam. Now, we haven't seen one in a couple of years. It's been similar to this. It hasn't been long enough that I would say, oh, okay, they're done with that, because we saw quite a few of them after this one. But we haven't seen it in a couple of years. Take that for what you will. Okay, I'd be ready. Okay, I'd be ready for it. I'd be ready for it. Sometimes it looks a little bit different, but when you see a question like this, electric force, you don't know any of the variables in any of the equations, give it a try. Give the free body diagram a try with the vector analysis, and maybe it'll work out. Yep, Ollie?